Multistage rockets. In this presentation, we'll discuss how to size a multistage rocket. So let's say we are given a specific impulse value, ISP, a delta V that's required, and an inert mass fraction, F inert. A single stage rocket is not feasible when you plug in the value for delta V, F inert, and of course the standard free fall acceleration, which is an exact quantity, namely 9.80665 meters per second, and find that this value is greater or equal to this value. If that is the case, your rocket is not feasible, it is not able to achieve the delta V that you're asking for. This equation is given in the Space Propulsion Analysis and Design Handbook on page 15, equation 1.29. Another way to interpret this equation is I can rewrite it such that I have delta V equals ISP times G times the logarithm of 1 over F inert. And so if I view this as a delta V equation, then one way to interpret equation 1 is as a speed limit. I am now using the equality sign in equation 1, and I've rearranged it to get delta V is ISP G log of 1 over F inert. And what this means is for a given rocket with known ISP and known F inert, as you approach this number, this velocity, the payload to propellant mass, the mass ratios goes to 0. In other words, your payload goes to nothing, or the propellant mass goes to infinity. You could view it either way. And if you think of burning up all of your propellant and then having no propellant left, how can you get any more delta V? You can't, except if you imagine in a fictitious case that you could actually take some of this inert mass, burn it as propellant, in which case you could get more delta V, but of course that's highly impractical. So let's talk about how multi-staging affects the calculations. Assuming that we cannot change the value of ISP or F inert, F inert being, again, the inert mass consisting mostly of structural mass. It's tanks and rocket nozzles and things that are not payload and not propellant. Anything that's not in the payload or propellant category is part of the inert mass. So if we look at equation 1 again, the only way that we can avoid the not feasible condition is to reduce the value of delta V on the right-hand side. So let me go back to that equation for just a second. So if we are given a value of ISP and F inert, and we find that ISP is less than the delta V we wanted, then if we could reduce the delta V that we need, we could create a condition where delta V was small enough such that our ISP was no longer less than this quantity. And therefore it would be feasible to get the rocket to go to that particular delta V, a lower delta V. And that's the idea of staging, is that we use two stages such that the total delta V is delta V of the first stage plus delta V of the second stage. So we've broken the problem up into two pieces. And we'll use F1 and F2 to be fractional values such that they add up to 1. So we could think of it as a percentage of the first stage, that is a percentage of the delta V covered by the first stage and a percentage of the delta V covered by the second stage. So then if we plug in these values of delta V1 and delta V2 separately into our feasibility equation, we may avoid the non-feasible condition. And so basically what's going on here is that you have a rocket that's consisting of two stages, burns the first stage to get a certain velocity, then drops off this inert mass, which is no longer helping but hindering, and then fire up the second stage. As the first stage drops off. Now the problem is, what should the values of F1 and F2 be? So that's called the problem of optimizing the delta V fraction. So for a two-stage rocket with identical values of ISP and F inert for each stage, it's clear the best values for F1 and F2 would just be set to 0.5 or 50%, so that each stage is covering half of the delta V. And this gives us the largest margin over the infeasible condition, or another way to view it is it provides the minimum total mass of the vehicle. And you might wonder why you would want to make the total mass of the vehicle minimum. And the reason for that is the cost of the rocket is usually related, proportional to the total mass of the rocket. So that's why you usually try to minimize the total mass. Now let's consider a case where we have different values for the specific impulse of the first stage. Let's say it's 410 seconds, and second stage 435 seconds, such that when you multiply G, we get the effective exhaust velocities of 4,022 meters per second and 4,267 meters per second. These correspond to liquid hydrogen and liquid oxygen propulsion system, but we notice that we're using a different value for the ISP in the second stage, and this is because as you rise in the atmosphere and the ambient pressure goes down, a rocket nozzle can become more efficient because the atmosphere is no longer hindering the exhaust velocity. So sometimes we get a slight improvement in ISP as the altitude goes up. So now we have different values for the ISPs, and let's also assume that we have different values for the inert mass fraction, and we'll use typical values right out of the SPAD handbook. Again, that's the Space Propulsion Analysis and Design book. And these are values from real systems. So we have the inert mass for stage 1 being 9.5% or 0.095, and of the second stage being 10% or 0.1. Now it's clear that when we're looking at how to do the staging and how to split up the delta V1 and delta V2, it's not clear that the values would be 0.5. In fact, it's clear that you would probably have a different distribution of percentage or fractional value for F1 and F2, since ISP and F inert are different. So what we're trying to do is pick the right value of F1 and F2, the fractional values of delta V covered. By the way, this is not to be confused with F inert, which is the inert mass. These are totally different variables. This is structure mass and nozzle mass and so on, tanks. F1 and F2 is the split between the delta V going on the first stage and going on the second stage. So the question is, how do we vary these proportions between stages and get the minimum total mass of the two-stage rocket, or for that matter any stage? Well, let's assume that we need a delta V of 9,000 meters per second. This is a typical value to get into low Earth orbit. In fact, you could, it's more than enough usually. And we'll assume that the these are just taken as arbitrary values. Let's assume that we pick F1 as 0.46 or 46% of the total delta V is done by stage 1, and F2 is the remainder, right? F2 has to be equal to 1 minus F1, and that's 54%. So now we can put in for the delta V1 46% of 9,000 meters per second, so we get 4,140 meters per second. And for delta V2, the 54% remaining of the 9,000 meters per second is 4,860 meters per second. Now remember that the propellant mass is calculated from this big equation. So you have m prop on the left and m payload on the right. And by the way, as we mentioned before, if the number downstairs approaches 0, that's where you're approaching the speed limit for that delta V. And that means that as this number approaches 0, the payload mass is going to larger and larger values. It goes towards infinity. And that means the ratio of payload to propellant mass is going towards 0. So that's what we're avoiding when we talk about the infeasible condition. We cannot have the denominator be 0. This must be greater than, this must be less than 0 for a feasible case. So you plug in our numbers, and let's assume in our case that the payload is 1,000 kilograms, 1 metric ton. In the examples in SPAD, by the way, they use 1 kilogram as their example throughout, and I'll tend to use 1,000 as a sort of practical number. And so we're going to plug in to equation 13 the values that we listed in equations 5, 7, 12, and 14. And what we're calculating is actually the last stage. Okay, so let me use my little vehicle here. So here we have, let's say, a 2-stage rocket. Okay, and I'm going to ignore the bottom stage for the moment and just calculate the first stage. Okay, so we'll view this as a single stage that's got to do the delta V2, right? This is second stage, so delta V2 and ISP number 2 and F inert number 2 will go into here. We'll calculate what the total mass of this is, the propellant mass, the fractional mass, and the payload mass, which we assume is 1,000. Once we've done that, then we're going to take this entire vehicle and consider it to be a payload, and we'll put that on top of the first stage. And then we'll compute the first stage with this part being the payload. So let's compute the propellant needed for the upper stage, stage 2, the top of the vehicle. We have 1,000 kilogram payload, and now we're plugging in the exponential, and upstairs we have the delta V that the second stage has to perform, 4,860 meters per second, and we're dividing that by the ISP times G, in other words, the effective exhaust velocity of 4,267 meters per second. Subtract 1. Here, 1 minus the F inert, which was 10% for the second stage, and then we have 1 minus, again, F inert, and then the same exponent that we had here. Plug in, and you get a value for the propellant mass of 2,779 kilograms. The inert mass is calculated from SPAD, equation 1.25 on page 15, by F inert over 1 minus F inert times M prop. We had for M prop 2,779 kilograms. F inert is 0.1 upstairs, 1 minus F inert. So this is going to be approximately 10%, 11% of this number. And so 309 kilograms for F inert, for M inert 2. And to know what the total is, we add up the propellant mass, the inert mass, and the payload mass, which was 1,000. Adding those three numbers up, we get 1,000 plus 309 plus 2,779 kilograms, or a grand total of 4,088 kilograms. So that's what the second stage does. And now for the first stage, as I mentioned, we will set the payload mass equal to that of the entire second stage. So now we're viewing the second stage as payload, the whole thing. And that is 4,000. So now we put M payload is 4,088 into our propellant mass equation. And using equations 13, 17, and 20 with values from equations 4, 6, 11, and 22, we get all these numbers that go into equation 24. to create equation 24. So we have a delta V of 4,140 meters per second. We have an effective exhaust velocity, the ISP times G, of 4,022 meters per second. We had an F inert of 9.5%, subtracting from 1. And down here again we have F inert of number 1, stage 1, and then the same exponential terms that we had earlier. Plug that all in, and we get a propellant mass for stage 1 of 9,067 kilograms. Now plugging into the equation for the inert mass of stage 1, we have again F inert F inert number 1 is 0.095. 1 minus F inert 1, and then upstairs we have mass propellant, and then that gives us 952 kilograms for the inert mass that we're carrying. That's the structure, nozzles, tanks, that sort of thing. Anything that's not propellant and not payload. And to get the total, we add up our payload, our propellant mass, and our inert mass for a grand total of 14,107 kilograms. So that's how we do one example of breaking the delta V, the total delta V, into two pieces, a delta V1 and a delta V2. And we represent that breakdown by the fraction F1 and F2. Now the question is, what's the best choice of F1 and F2? And so here we have, again from the SPAD book, an algorithm of how to optimize that delta V fraction. And whenever you say the word optimize, you should say, what is it that I'm making best? What is the quantity? And what we're doing is we're making the vehicle mass minimum, okay? Because we associate vehicle mass with dollar cost. It's not always exactly true, depends on a number of things, but to the first order, the mass of the rocket is going to determine the cost. So it's very relevant in the cost calculation. So here's the algorithm to compute the breakdown of the total delta V into two pieces for the two-stage. So we can choose a range of F1 and increment it by some delta F. So we could say, let's say 20% of the delta V is done by the first stage, which means 80% by the second. Or 30%, 40%, 50, 60, 70, 80. So we have this range of F1. And we start with the lowest value. We can count through them in our algorithm. F2 is just 1 minus F1. So if we, like I said, if we pick 20% for F1, then F2 would be 80% for that particular calculation. And then we put in delta V1 is F1 times delta V. Delta V is the total that we need, the 9,000 that we had before. And delta V2 is F2 times delta V. So now we have the delta V's to go in there. We plug these terms into our propellant mass calculation and calculate the inert mass as we showed, and finally adding the payload mass, we get the total mass of the vehicle, MI, as we demonstrated for a particular case. Then after doing that, we save that quantity, and then we calculate a new value for F1. We just add some increment to it, and if we have not completed already the final value in our list of quantities, if we haven't done 0.8, then we continue on until we finish. So we go back to step 3, calculate the F2, and then calculate a new mass, MI. When you've done this, you end up with a plot like this. Here is the first stage delta V fraction ranging from 0.2 to 0.8, okay? And then we can use a lot more values than every 0.1, as I suggested, to have a nice smooth curve. And what we have here is the initial vehicle mass, and I put it in 1,000, in thousands of kilograms. So we just saw in our first example with F1 as 46% that we had a little over 14,000 kilograms for the total rocket. And in fact, that is the minimum. And if you vary away from that ratio, that is from F1 being 46%, then you'll have higher mass costs because that's what's on the vertical axis, the total mass cost. There are many ways to do this kind of calculation, and so this simple algorithm is just one to give you a concept of how it works. So don't feel constrained to do it only this way, but this is a nice way to understand it. So what about a three-stage rocket? Well, in that case, to minimize the total vehicle mass of a three-stage rocket, we need to compute the surface, mi, which is now a function of two variables, f1 and f2. And then f3 is determined by taking 1 minus f1 minus f2. And so we have this surface, which is a function of two variables, and we're seeking to find the minimum mass down here, plotting f1 and f2, and the mass is a function of those two axes. So it's a surface of 2 degrees, and now we can consider what happens for n stages. In that case, we must compute an n-1 dimensional hypersurface. So in that case, we have the total mass is a function of f1, f2, f3, all the way up to fn-1, and the value of fn being determined by subtracting these values from 1. So that's how we get an n-1 dimensional hypersurface. And that completes the presentation on multistage rockets.